All right, let's go ahead and get started. Good morning. My name is Steve Gordon. I'm the chair of the SIG HBC Education Outreach Committee, and today we have the pleasure of having David Joyner from Kean University to tell us a bit how he uses several tools in teaching computation topics. So without further ado, David, go ahead and introduce yourself and begin your presentation.
Thank you very much. So I think everyone here knows me, but I'll introduce myself anyway for the purposes of the recording. My name is Dave Joyner. I'm a faculty member in the computational science program at Kean University in New Jersey, and have been since 2004. Before that, I spent 5 years with the Schroeder Foundation. Before that, I like to think of myself once upon a time as an astrophysicist, but those particular projects seem to be fewer and far between these days. We teach courses in our computational science program at Kean in a variety of different things, of course, but specifically high performance computing. We have a high performance computing class we run at the graduate level in a 5-year program, master's and bachelor's combined. And we also have an introductory course in programming that's Java based so that it meshes with our computer science department. And I want to use those kind of two classes as particular examples of some things we did, partly to shift towards handling COVID over the last year, but also to think about how to make better use of different sort of computing resources that our students have. Our students are around 50% first generation. We were recently designated as an urban research university. We do have a fair number of students who are below the poverty level, and concerns over what resources we can provide are always an issue. Anything we can do to save a dollar for our students on a textbook, on a computer, piece of software is always something that's really important to us. So we have those as constraints as well in this. So basically, how do we start thinking about the tools that are going to help this? And let me see if I can manage to get my screen shared. And hopefully this will work. Is this showing up properly on the screen for everyone?
Yes.
So as probably you can guess from the title of the talk, the primary tool we've gone to for this, certainly that I've been using a lot, is CoLab, Google CoLab. If you've not used CoLab before, CoLab is a cloud-based Jupyter notebook managed by Google. Google has a couple of these products, both of which have a very substantial free tier, but you can also pay more to get a non-free level. CoLab and Kaggle. Both of them are very Python-centric in the way that they work. And for our students, a lot of our computational science, I'd say about right now, 75% of our computational science students wind up actually going on and doing work in data science. So having experience at these notebook environments is great for them as they go on and find themselves in industrial environments where they're working, and at that point with higher security level and different hardware with Databricks and SageMaker, but kind of across the board, this idea of these data science notebooks as a key environment we want our students to learn has been really important to us, and certainly a skill that they need. But CoLab in particular, well, I shouldn't say in particular, because actually I've tried these things on both CoLab and Kaggle, and they work really well on both. And Databricks and SageMaker is going to depend a little bit more on how it's configured. But for the student standpoint, CoLab and Kaggle could be used interchangeably on these things. And I've tested them out on both. The CoLab's what I'll show today. So when you have your CoLab session, the key thing is you're connecting not to an install of Python or something on your own personal machine, but to a virtual machine somewhere in Google's cloud. That virtual machine will be running these days probably Ubuntu 18. There's ways to check that, but lately, essentially every single CoLab notebook that I start up, when I check it, I'm running Ubuntu 18 right now. And even without paying for the higher level tier, while they've got some things you can pay for to get like better shell access and things built into it to that virtual machine, you can run shell commands in your notebook, and you can easily access the file system both through kind of a drag and drop interface in the notebook, as well as a command called write file. All of the Jupyter and IPython, what they call their magic commands for the IPython notebooks and the Jupyter notebooks, work just as well in CoLab, as well as, again, our shell commands on the underlying virtual machine. So the idea being that we can, in this one environment, get our students, as long as they've got an internet connection, doesn't take a particularly high-powered one, and a browser that'll run JavaScript, they can, and a Gmail account, which they all have. They can have access to, multiple virtual Ubuntu instances connected to GPU or TPU hardware that Google makes available, again, all in the free tier. They can write to that operating system underneath, and they can run Unix commands. And those Unix commands can also be things like apt-get install, right? So they can configure things in very complex fashions. Again, on a completely free resource with something that all they need is an internet connection on a machine with a JavaScript capable browser for all of our students that are coming in, who are coming in with, say, Chromebooks or certain types of tablets. No matter how much we tell them, we're a laptop program, you've got to have a laptop that will do this and that, we still get a lot of students coming in Chromebook situations. So it allows for something that'll work with that. So CoLab has been, I think, really kind of key for us for that. And let's see if I can do this and still kind of have everything show up. I'm not 100% sure how well the font size is going to come through. I'll try to zoom as appropriate so y'all can read and see things. If at any point fonts need to be bigger, just kind of let me know. So the way I kind of think of it is the glue for all of us, right? If we can execute a shell command, write to the file system on an Ubuntu machine that we can configure on the fly, that's a lot of stuff that we can do, right? That goes beyond the traditional open a Jupyter notebook and run some Python code. But you do still have that kind of Python backend. I've also kind of worked with some students on things where they can do some configuration to have a kind of a native CoLab notebook running in R, in Julia, and a few other languages. But that's not the approach I want to take with this. The approach I want to take with this is just simply this idea of our students who we want to have Linux experience anyway, interacting with a virtual Linux machine, but using the CoLab notebook to do it. So quick run all in the background here to make sure everything's up to date. So again, just a few things again, what you get with Google CoLab. Again, this is not actually for getting rid of space on this machine. I think this is one of the first times ever I've uninstalled Python from a machine to save space. I don't even have Python running on this machine. So this is a zero configuration environment. Everything is just what's being provided to me through my Gmail account. And in terms of settings that the students can do, there's some things in terms of you can change the editor, change font size, line numberings. I think are great to be able to turn on and off. For my students, and this is just a really silly thing, but for using this in a classroom setting, just a great fun icebreaker. You can set a mode where little cats or dogs will walk across the top of your screen. And that sounds so silly, but let me tell you, in terms of kind of breaking the ice, particularly in like a freshman class setting, it's, why are there cats? Oh, well, let's talk about this. Anyway, so there's some fun things there you can play with. So if I look at this, and again, I'm just going to, and I'll talk about these shell commands a little bit more, how you use them. But here I'm just going to real simply use a shell command, and my shell commands all start with either an exclamation point for a single line shell command, or I can use shell magic, which is %% shell Depending on, and that'll work again across all of these notebooks I've tried. It's worked on Databricks, worked on Kaggle, worked on CoLab. There's also things like you can try %% bash if you really want to bash shell. Your results will vary on that one, but I've found %% shell and the exclamation point to be consistent across every one of these cloud-based Jupyter notebooks I've tried. So again, I'll just check my operating system release and my kernel version. So by default, the machine running underneath this, again, whatever, and it might change a little bit based on what you pick up that day in Google's server farm. But generally the OS I've found to be very consistent. I get the same thing each time. So we're running again 18045, kernel version 5.4.144. And the other command that I use a lot in these CoLab notebooks to go beyond just the traditional Python programming cell that so many people are used to, again, is that write file command. So what happens when I execute a command with that write file magic as the first line here? I see %% write file hello.java with some stuff. I can go over to the side of the screen here, check my file system. There's a few extra things here because I did a run all on the notebook already to make sure it was all working. But when I did that, it's going to write to the local file system. And this file system, again, it's all cloud-based. And if you ever drag and drop things into the file system, it'll even warn you, this is a, containerized notebook. When you close the notebook, anything in this file system goes away. But I can check on that and see, I've created my file here. And when I first started doing this, before I even started using this to do CUDA things with my HPC class, it was just trying to find some consistency for my introductory programming class, where we had to use Java as the language for prerequisite purposes with our computer science department. And, after fighting in previous years with how long I knew it was going to take to get a classroom of people who all brought a completely different laptop, some of whom tried ahead of time to install Java, some who didn't, every one of them who installed a different version of Java, every one of whom installed a different version of Eclipse, some of whom couldn't get Eclipse running, in terms of that one consistent environment, was to say, hey, can we just get this running in a virtual machine like this? The idea is great. So if I can write a file to the operating system and I can execute a Unix command on that operating system within my Jupyter style notebook, that could be, well, let's write our code, let's compile our code, and let's run our code. Again, also reinforcing the write, compile, run cycle for those introductory students. And at that point, once I've done that, why Java, why C, why CUDA, whatever I kind of want to do. Initially, when I had looked at, hey, I could use CoLab notebooks for other things, some of these things like where people have versions of CoLab to say natively run Julia, like you can do in a regular Jupyter notebook. I started kind of looking to that, but you know what? Hey, if it's just write it and then run a compile command and run it, this could be any language we want, right? So if I want it to be C, right, I'll write, C++, and then run it. And again, as I'd said, there's two primary ways when I want to execute something on the underlying shell. There's the exclamation point character within a compute cell in CoLab, where I can also use a full cell magic command, %% shell, the top of the command, which basically says, instead of Python, all of the lines in this cell are just commands running on the underlying shell. And that can be a compile statement. It can be a listing statement. It can be a change of directory, though that's a little bit of a weird one, that directory changes will not persist from cell to cell. So there's a few tricky things like that you got to get used to. But again, you can write files, you can run Unix commands. You've got a virtual Unix machine. That opens up a lot. A few other kind of things before I kind of show specifically some computing examples we've done with CUDA in particular and with Java. You don't have to just pick one language, one way of doing things with these CoLab notebooks. The default language for these compute cells is Python. And you can mix and match shell commands and Python commands in the same cell. For example, let's say, for example, I've got data on GitHub or on a web server somewhere that I want the students to download and then process. And I want to be able to just execute a wget command. Well, great. I could have a single shell command that's just going to do wget and download the stuff. But suppose, it's a lot of stuff, and I only want the students to download it when they first run the sheet. I don't want them to have to kind of keep downloading extra copies, run out of memory, things like that. And I want some logic of only download this or only unzip this if it hasn't been done yet. So I can use all of my standard kind of Pythonic way of doing that. Hey, let's check and see, does this file not exist? If it doesn't exist, now I'll use my shell command to do that, and maybe a little more Python to kind of show that. And when I run that, and actually let me do we'll force this. We'll do a factory reset runtime on this. So we can see that this really is doing this as I do it. I'll connect. Again, I've got nothing except my sample data in the file system. And execute. I see it runs my wget, downloads it. And I can go back over here and see that the file has loaded. So, and to me, again, this is one of those things where I was like, okay, I knew I could run a shell command like this inside of these, Jupyter style CoLab notebooks, but being able to kind of mix and match the native kind of Python code style of doing these notebooks with the shell commands in a single cell. Wow, that's pretty powerful. I can do a lot of cool stuff with that. Right? And what's more, when you execute these shell commands, particularly these exclamation point single line shell commands, you can directly capture the standard output of that, not just say print it out to the screen, but you can directly capture the output of that, bring it into a variable in your kind of, the Python side of your CoLab notebook, and then go and work with things and execute things with that. So anytime you do these exclamation point shell commands, standard output is essentially going to the stack, which means you can capture that and then work with it. So for example, here, if I just do a standard Linux echo, these are some words, and if I were to do that just as a shell command, what would that do? Just echo something back to the terminal. But if I do that inside of my shell command with it set equal to a Python variable to capture it, mind you, I'm still going to print to the screen, but notice now I've captured that in that Python variable, and I could do things like each word equals words dot split. Actually, technically, this is an array of words. 0 split on space. I think this is right. No syntax error. That's good. So I can go through and I can start manipulating and working with the results of standard out from a shell command inside of, say, a Python cell in terms of how I go back and forth in doing this, which is, again, I think really cool. If you need to have software on your virtual machine that isn't there by default, and it's getting harder and harder to find stuff that CoLab isn't putting into a default package. I started going through and looking at, oh, well, I'll run this or I'll run that as an example, and I was kind of putting this together. And at this point, they're all just kind of standard in the CoLab shell. I had to basically go to FFTW before I found like a software package that wasn't just installed by default already. But I can go in and I can run an apt-get, say, for example. and modify the software configuration of the machine. So if there is, say, for example, say you want to do something with CUDA where your version of CUDA by default needs to be upgraded, or you want to download some extra development packages, or you want to have it packaged with some other standard science package, your shell commands have effectively root access, right? When you do these notebooks. So if you want to install software on the fly, again, generally easier if it's something available through apt-get, you can do that. And this is, I'm not going to scroll through this a bit because it's kind of a lengthy piece of code in terms of this, but I just grabbed basically to test and see if that worked for this notebook. One of the test codes from FFTW3, and I'll write that cell, compile it, run it. And again, so now we have on a CoLab notebook, modification of the base operating system to install software underneath with a simple apt-get as a shell command, edit the code, run it, right? So again, and all of this at a zero cost, zero install barrier for my students in terms of the examples they can run. And of course, you know, because Python's the default, if you need to install something with pip as well, again, a shell command to do a pip install to extend the base Python stuff works super well too, right? So this is really, again, the kind of the fundamental glue that put together my thoughts on, okay, how can we use this for HPC examples? How can we use this as well in my introductory class of these cloud-based notebooks? And again, because it's all cloud-based, it's also shareable. I can download as IPYNB. In fact, this is the way I have all of my students turn their work in. I found that this is the most reliable way for them to get things to me. We always run into problems trying to share the cloud-based stuff with other permissions, right? But I can have them download their IPYNB, upload it to Blackboard, and I can get at it, run it real easy for testing. So, so that's kind of the, again, my going into this with these CoLab environments is if I can write to the operating system, if I can install things to the operating system if necessary, if I can run things on the operating system, I can do a lot more than just run a Python cell, right? Any questions on this so far? Awesome. Also, and I don't know if I sent this link out, but let me make sure this gets into the chat as long as everyone's here. I've got these slides and all of these worksheets I'm showing today available to be shared. So feel free to kind of go through and look at these, and I'm happy to add to these with some other examples that I can find. I tried to dig up a few things on my hard drive and didn't find as many of the things as I was remembering as I would have liked, but I got a few things here, and you can feel free to take any of these sheets and reuse them as you like. We used this as a big piece of how we managed some of the CUDA modules with the Blue Waters Capstone Curriculum project as well. That's not yet released. We can ask Aaron, how's that going? But when that comes out, again, a lot of those you'll in the CUDA module for that will be done using these CoLab sheets. So in terms of combining specifically this with the GPUs that Google's willing to make available. And again, actually, I'm on an Alienware laptop. I do have a GPU somewhere on this machine, but I promise I'm not using it. I was going to say I have no GPU on this machine. I do on this particular one, but I'm not using anything from this local machine for this. I could be doing this again on a tablet if I want, on my phone. And, well, phone gets a little tricky because the screen's kind of small. Touch screen and JavaScript don't always work as well as you'd like. But again, when I look at my runtime, a key thing here under runtime and runtime type is your hardware accelerator. So for the free tier, and this is true with both Google CoLab and Kaggle, which is also a Google product. For the free tier, you can run up to, I think, 4 or 5 notebooks at a time for up to, I believe it's either 12 or 24 hours. There is a time limit when the notebook will time out. Um, but you can run up to 4 or 5 at a time. It used to be you could run 2 of them with a GPU or a TPU resource simultaneously. They've dropped that to 1. So you can only run 1 notebook with a GPU attached and connected at any given time, but that's per account. So again, so if I'm teaching, that means I can run something to demonstrate to students, and every single one of my students in the room can do this. I mean, so that's, if I've got a class full of 20 students and me and all the 20 students, that's 21 GPUs that we've just borrowed from Google for their free tier. We just got an approval from our board of trustees to upgrade our campus compute resource for a system that's going to have 20 GPUs on it to share across our entire campus, right? For research purposes. Here, and again, we have a classroom situation where if I had 30 students, I would have 30 GPUs for the students. It's 1 per student, and they all do it through their account. So that's a lot of GPU hardware we can throw at this for the free tier. And again, the tensor processing units as well. So if you have examples where you're more interested in doing some TensorFlow type material on a tensor processing unit, that is an option with this. But what we've been doing is using the GPU. So when you use this, it will reserve this session as your kind of 1 GPU session that can be running at any given time. If you don't have that GPU set in the hardware settings, it'll be like trying to run CUDA on a machine with no GPU, and you'll get a few errors. So that's definitely for my students. The first thing I always ask, kind of like, if you checked for typos with syntax errors, this isn't working. Did you check to make sure the GPU is turned on? I have a few repeats on some of the shell stuff here in this particular worksheet if you borrow it. So I'm going to scroll down just a little bit to the CUDA specific stuff. Again, without any extra software installs, I didn't have to do apt-get install CUDA 11 or anything like that. If I just do, shell command, tell me my NVCC version. This will take a little bit the first time because I am connecting and initializing, and it's not yelling at me that I've got another GPU in use. So by default, 0 configuration. We've got NVIDIA CUDA compiler installed to run with our CoLab notebook at release 11.1. And usually they keep it pretty well up to date in terms of, latest stable release on these. And I can also check to see, again, I'm just using shell commands, the same things I would use to check if I was sitting down at a Linux machine. I could check to see what card did I get assigned for the purposes of this sheet. And I can see here that what I've gotten is a Tesla K80. This is one area where I found it's a little bit of a sticky point working with my students on this, is because we're using Google's resources and you get kind of what you get, you're not guaranteed that you'll get a very specific graphics card from Google. It'll be a range of things. And I believe the K80 is the least powerful card they will ever give you. I have occasionally gotten A100. That's kind of sweet, but not often. But I've seen kind of different variations of which brand, not which brand, it's going to be NVIDIA, which model of GPU you get assigned when you ask for one of Google's GPUs. This actually is an important thing to check, because when you start running examples with CUDA, it is almost definitely the case that you will want to use something more than just kind of the vanilla compute level 1 default compiler settings. And the range of hardware that Google will provide is such that you do want to match your compiler settings to the card. It's a simple thing. It's a simple thing for the students to check, but it's another one of those things that can be a little bit of a stumbling block. And it's also, you might see a few warnings if you get one of the K80s, because from the highest level of what they're willing to install to the lowest level of what they're willing to install, you might get a deprecation warning, thing like that, something like that, which we're gonna, if we're using a K80, we're gonna see some deprecation warnings in a little bit. I have for this sheet, and feel free again to copy this and use it as you like. One of the things I found was that the default install of the CUDA libraries on a CoLab sheet, while it does include the compiler, it includes the development libraries you'll need, some tools for querying what kind of device you have. The device query program that comes with the CUDA sample package, when you do say a full install of the CUDA toolkit on a Linux machine that you have locally, that, I'm assuming for space reasons, does not get installed. So rather than going through and installing it, what I have here is just a slightly modified version of the device query example from CUDA samples. I believe, given the licensing rights and the fact that I've attributed this is free to share in this way, but basically this is a slightly modified version of what I took from helper_CUDA.h of their device query machine. Sorry for kind of a lot of hideous code. If you don't want students to see the code, you always can, like you can with any of these sheets. We can, sorry, I'm gonna have to make the screen a little smaller for a second. If you want to, we do have the option of making this field a form, which is a great way to hide some code, because forms allow you to hide your code. So as long as I run it, it's fine. It'll still write. So these write magic things in the shell commands can be hidden under a form in this as well, if you feel like you're, showing more kind of code the students don't need to see than they want. But again, so this is just the device query code from the standard CUDA samples, and I can go and I can get a little more information. Notice I am doing a shell command, NVIDIA CUDA compile, output query, query.cu. That's my code that I just hid in here. And I can get a little more information. In particular, and this is important because it's not part of what we get out of the NVIDIA SMI command to get the card information. I can look at things like, what is my warp size? I've not had a warp size other than 32 in a really long time. Having said that, it's still always, I think, important for my students to always have them think about checking the warp size whenever they're thinking about kind of optimizing any CUDA code. But also another kind of key piece of information that I was actually really surprised isn't in the NVIDIA SMI command. What's their total number of cores? Again, so by using that query command, the students can check, okay, what device was I given? What's the warp size on that device? Hopefully they'll, make reasonable choices that don't get broken by things like maximum dimensions of a given block, but they've got that there to check if they need to. And again, really key for what sort of speed up they can expect. How many cores do they have available, right? And notice I was able to do that because the query command doesn't really do anything fancy. I don't need any sort of extra kind of hardware information in that compile statement. But it does again tell me this is a Tesla K80 GPU. And I've put this link here in this sheet. So if the students need to, they can go in, they can check, all right, for a Tesla K80, the default compute capability is 3.7, right? Like I said, I've gotten everything at this point from a K80 from Google to an A100, where it's just a range of compute capabilities from 3.7 to 8.0. They're currently, my other one I actually usually get. I usually either get a K80 or a, so I'm going to find it here. My other one I tend to get a lot is, not the M60. It might be the M60. I tend to get that a lot from Google. Anyway, but again, so you know your default compute capability. So if you need to specify that to get things to compile right, you can. So, and it doesn't take much with your CUDA code before you're going to want to be able to use a properly specified compute level setting. And in particular, if there is one command that I find in a classroom setting is vital, and that's not a command I would typically use in production code, but something that I find for a classroom example, I absolutely have to have, and for debugging, I have to have, it's a printf, right? And if I can't run printf, and if I can't run printf from within a kernel on the GPU when the GPU is executing things, debugging and knowing whether things are working right gets to be really hard. Printf was not part of the default set of CUDA commands back at compute level 1. So this becomes immediately for me something that in a classroom setting, if I am not specifying my architecture settings, I can't use any of the more advanced stuff. And that means I can't use printf from within inside of a CUDA, from side of a CUDA kernel, right? So the fact that I means that when I do my hello.cu code, again, notice I'm just using a write file statement to write it to disk. Other than that, it's just the same CUDA code that I would be running on a GPU-enabled Linux machine.
Excuse me, Dave, can you increase the font size again, please?
Oh, yeah, sure. Sorry about that. Thank you for pointing that out. Better?
Good, thanks.
Awesome. So yeah, so this is, what would you expect from a first day teaching CUDA in an HPC class? Let's start with hello world. I've got my global kernel that's going to do nothing but print hello from the GPU. I'll have a main routine, which is going to call one block with one thread per block of that kernel and do a device synchronize. Device synchronize is necessary if you use printf inside of a kernel, because otherwise you're not guaranteed that the kernels will all flush their print buffers. And you may get print statements that exist in a buffer somewhere, but never actually make it to the screen. So I'll write that to disk, I'll compile it. And again, notice I've matched that compute architecture to the card that I have. I run it. I do get a deprecation warning when I get my K80s because CUDA 11 is kind of ready to move beyond some of the old compute levels. But on the other hand, I've got to use the old compute level, because if I try to use one that's more advanced than the Tesla K80 can handle, then it's not going to work. Now, let's say, for example, I had a different card that required compute level 5.2. Notice that I can't try to run compute level 5.2 and get it to work properly on this K80 card. And unfortunately, it's not going to give me super obvious errors. This has always been the case with teaching CUDA is if there are errors at all, those errors tend to live somewhere in the GPU and don't print out any useful information to the console. So students will often just get strange results, right? So this is always something for me that I check and make sure. What device did Google assign you? What is its properly allowed compute level? And again, for me, that is, and for a lot of my students, if they just kind of randomly try 3.7 and 5.2, that would cover probably 99% of the GPUs that I've ever been checked out from Google when running one of these CoLab sheets. I change it back. Everything's working. And again, we can have students start playing around with that and really make sure those print statements are working. So here we have, again, fairly straightforward, a kernel that's going to do nothing but call a printf command just so that we can check and see that things are working the way we expect. We'll print the thread index and the block index. We'll call that kernel with 3 blocks and 4 threads per block. And again, I'll do a device synchronize, because if I do have any print statements in the kernel for debugging purposes or for teaching purposes, if you don't synchronize the devices, you don't flush all the print buffers. Write that to disk. You'll notice I even here have a commented out compute 5.2 from a prior time when that was the one I needed for the card I had that day. I'll redirect output and CAD it to take a look at it. I often will, with these sheets, I'll often redirect output, same as I would on a Unix command line, because if there's a lot of output, I might want to go back and look at it later. This also is, I really like this. I'll say more for this when I talk about my introductory Java class, as a way to start doing input output without having to, teach file writing and file reading, which I think is one of the more challenging introductory topics to teach. But they can always go in here if I want to. I can download this when I'm done, turn it in, So, and again, it's what can you do when you have the ability to write and execute on someone else's Unix machine with super user privileges and the ability to install software, right? With a GPU attached. Again, fairly straightforward in terms of how to do this. All I had to do was turn the runtime to GPU. I use the write file command to write my code to disk, and then I just compile and run as I would normally. And the only really kind of tricky thing that I have found in doing this is checking to make sure that I know which card I have and making sure that my architecture setting is matched to that. And as long as I've done that, pretty much every example I've tried, I found runs as smoothly as I was running on a local machine. Any questions so far?
I had a question just about kind of like how much of this you tell your students about, like as far as, that you're kind of switching between Python and Bash commands and, and like the concepts of GPUs, I guess.
So for the CUDA stuff in particular, I would be teaching this in our CPS 5965 high performance computing class. It's a master's level class, which we tend to have a number of senior level, occasionally some junior level undergrads also taking. Sometimes they'll just take it as undergrad credit. Sometimes we'll co-list a special topics at 4,000 level. So these are students that in my mind ought to be able to handle this. And in fact, the juniors and seniors who've just been through 4 years in which they've had activities that had to be done on a local Unix server, that have a lot of Unix experience, generally they're going to get that right away. And this kind of meta idea of, hey, we've got an interface to some virtual Linux machine and this is what we're doing, they'll pick up on that really fast. Where I have had some issues is, so this is a class that we teach to the computational science students. It's also an elective for a graduate level standalone, a master's level standalone IT program that the computer science students, the computer science department on campus recruits a lot of students into. Those students who are coming in not straight out of a bachelor's degree, more of a gap, coming out of career to try to bolster some IT or some computer science knowledge, their Unix skills tend to be a lot weaker. And in fact, we get a lot of students from that background who have really been doing more kind of like web design type stuff. That it's been a while since they've programmed or used any sort of, to the degree they're doing anything, they're doing front end stuff. Or they're doing database stuff. And when we start getting into, all right, this is Unix and this is how you compile something, right? The idea of compiling code, I have found with those students, is a step we have to talk through. And it's a little trickier with them, but it's still, at the point I'm teaching high performance computing, this is at least an upper level undergraduate class, if not a graduate class. So those concepts of how everything fits together to me, I think is really important. So I absolutely go into it. I'll change my answer slightly when I talk about what we do with our intro Java class. But not that much, because we have a prerequisite requirement with that class that we're essentially creating a computational science version of computer science's first semester Java class, which also, we have to match all the prerequisites. And that also has a content requirement that they get their first experience in Unix. So the ideas of some of these Unix skills are still key, and we still want to reinforce.
Mhm.
So a little more gently, but even then, yeah, we definitely do that. And I've got an example of, for that intro Java case, really where I like to mix up the Java and Python a little, and that I think is actually pedagogically appropriate for an intro Java class with a computational science focus. Any other questions on that?
I was going to ask at the end, but I might as well now. So how much acceptance is there among the faculty of this approach, and or how do you promote it and encourage and help other faculty use these tools?
So in terms of kind of some of these hacks of, hey, we could use CoLab for other things, we don't have it. So our computational science program is not housed in the computer science program. So we don't have as much control over what, say, the computer science department is going to do in their courses. Having said that, when I've on a one-on-one basis showed like, hey, have you ever tried doing this? I think the general response is, wow, that's really cool. All right. But in a lot of cases, there's entrenched, well, for this class, we're already doing it on the Linux server that the student has an account on, so we'll go do this on that machine. I am the only person on campus that teaches the HPC class. So definitely with the HPC class, there's 100% adoption because that's me. In terms of where we've been looking at notebooks in general, we have, over the last 3 years, we had started our computational science students off with a mixture of Java as a strictly typed compiled language and MATLAB as a scripting language. And we did switch largely with the shutdown, partly because of these issues of resources for students, and partly because we suddenly found ourselves having to hire a bunch of adjuncts that year. And the adjuncts we hired all had Python experience, but not MATLAB experience. We switched our kind of shell scripting environment where we want to do simple things like that. We switched from MATLAB to Python about 3 years ago, and all of our Python stuff is done through these CoLab notebooks. We've had on the computational science side of things, full adoption of that. All of our students, the first tool they'll bring up if they're doing any sort of work is going to be a CoLab notebook. And again, it's easy for us to share. We can have shared editing on it. And again, whether we're doing Python work, which a lot of our stuff we do in Python, or something else. I've got a project with a student right now. She is working on a object detection code where we're trying to take stem cell data in 3D and detect and characterize the cells, and basically use a simulated annealing, move a little target cell around the 3D data, find where you fit, move to the next one. And she's doing all of that in CoLab, right? Rather than run things on a particular server somewhere, or rather than having Eclipse or Visual C++ installed on our machine, we just do all of that work in a CoLab notebook, and we can edit the C code in it, and we can share it. So as I've had other faculty and other students work with me on these types of ways of using these notebooks, I just find the adoption is really fast. Did I answer the question?
Sorry, I couldn't hit unmute. Yeah, thank you.
All right. So let's see. What's our timeline, by the way? We run till 12, right?
Yeah, we have about 10 more minutes left or so.
So let's see. I want to run one kind of real quick example I like to use for the classroom in CUDA real fast, and then I'll give one Java example, I think. So one of my lessons that I like to work on throughout my high performance computing class, an example I always kind of go back to over and over and over again, is creation of the Mandelbrot set. I think it's great in terms of the need to do some load balancing on it. It's a simple algorithm that's easy to describe. It's not hard to code. It's not hard to give students a pre-written code and have them modify it. So it's kind of one of the ones that I use a lot. I've got a code that I've been using for years for this that draws it using libgd. So again, I do have to do a really quick install of the libgd development libraries, but again, it's a single apt-get install line. I give the students some code that will essentially calculate a bunch of pixel values using a standard nested for loop, going over the image, decide on how to draw things, write it to a buffer. The main routine handles some input and output, prints out, echoes, what was done. We calculate the pixel values, use a clock timer to figure out how long it took just to do the pixel values. And then I'll draw the image, write it to file, we'll print it. And again, some code that I give the students ahead of time, that's basically just some GD code to take pixels and draw them to a PNG file. And again, I'll let this be pre-run because this one does take a little while to run. So here we have, we create an image, and the students can specify, how many pixels, a square image, how many pixels wide and tall, what's their range of where they want to calculate the Mandelbrot set, what depth will they use to time out. And then again, I'll mix a little bit of Python here, just enough Python to display the image so that they're not having to kind of go over to the screen and click on things here. And they can see, okay, great. I've got my image created and it took, a minute or 2 minutes or however many to do that. And then generally at this point in the class, we will have talked about how to take, a single for loop or a nested for loop and rethink that in terms of writing a kernel for use in CUDA. And this will be a homework assignment for them. And the expectation is they would be able to then take that pixel value routine, rewrite it as a kernel, think about how they're going to index it, what's going to look different about it, what's going to look the same, modify their main routine to handle any sort of device-based memory creation, copies to and from the device, to run it with an appropriate number of blocks and threads per blocks and play around with that for timing purposes. And then tell me, okay, hey, I got this to run. I got this image, and sorry, I ran this with slightly different things. And so this one took me, say, 254 milliseconds instead of 1 minute or 2 minutes to get my image of the Mandelbrot set. So this has been, an example I've been using for years with my students, but really only the last couple of times I've taught the class where we've been doing it inside of these notebooks. And I found that that's just a really, really powerful example, both from the standpoint, again, of getting them to practice coding it, seeing the speed up, which this one does have a fairly nice dramatic speed up. And they can even start going in and playing with optimization of the number of blocks and number of threads per blocks, which I know I had here just a second ago. Where is it? There, right? Playing around with things like the number of blocks and the number of threads per blocks to really look at, how much of there is an impact. Say, for example, if their number of threads per blocks is not a multiple of the warp size, is that a good thing or a bad thing? And how do they want to balance those issues? So this has been a really nice example that I like to use. Let's see, 1056. I want to show at least one kind of just introductory programming example. I'll jump straight to this question of, do I get into mixing the Python side of these notebooks with these kind of hacks to be able to use other languages with it? the number one reason I love to do this in an introductory class, I am tied to Java as an introductory language, right? Because of the computer science prerequisites I have to match with, I have to use Java as our primary strictly typed teaching language. And again, I recognize why computer science likes it as a language, and it's certainly faster than vanilla Python. Even if it's not the fastest language around, it's fast enough for most things. So I'm happy to have that first class be a Java class. But anytime we start working with Java, and the same thing's true, I suppose, with C, is the lack of plotting tools, right? If I want to do this for computational science students, I want to use math and computational science examples. And not just being able to plot a result is really, really frustrating. And getting Java to the point where we can do plotting with it is a pain. I've got to talk to them about, okay, let's take this extra library, load in the jar file, link against it, bring it in, learn how to use that jar file. At one point, I finally just wrote my own set of plotting code in Java to make it easier on the students. But in general, if I just want to have a result, by doing it in a notebook like this, I can do something like say, okay, here's your Java project you've got to do. And it's going to create some information, right? And this is really kind of cheesy. I got a linspace command here. This is just for example. I got a linspace command. I'm going to linearly space some values. I'll say y is math of sine of x, and I'll print it out, right? And that's all I'm going to do, right? I'm going to have my code, and this could be any example I want to have the students do. For my purposes today, I'm just going to make, x is x and y is sine of x. And I'll print it out in some sort of reasonable format. And again, curriculum-wise, all of this is stuff that I want to teach my students about anyway. I want them to know the math libraries. I want them to know the difference between print and print line and format, right? And to know how to create a file in a way that works. I want them to understand the edit, compile, run cycle. And I want them to be able to do in Unix a command line redirection as a simple way of doing input and output. Once I've done that, hey, I could have the student download this, open it in Excel, make a plot that way. Or I could just read that file locally in Python, using, the pandas in matplotlib, throw it into a plot and show it. And now the students can have essentially the Java that I need to teach them. The speed of Java, which for some things is noticeable compared to Python for these learning examples. But they can do their plots and they can see the results and they can do it in a very immediate way. And for a lot of this, as long as they can do it to a prescribed format, I can give them this code ahead of time. But again, we do a kind of a two-language approach anyway, where the students are learning a strictly typed language and they're learning a scripting style language. And since they're already learning Python in another class anyway, as their kind of scripting language approach, as part of their math classes, it's a really straightforward transition for them to do that. So definitely, even at the introductory level, that kind of mixing of what is a CoLab notebook, why do we use it, and the idea that we can do this using the underlying virtual machine, but we can also kind of jump back into just using this notebook in its traditional way. We do talk about that with our students, and I do that quite regularly. So trying to think. So those are my examples. So any questions about that?
Any questions for Dave? Feel free to unmute and ask it, or you can put something in the chat window if you prefer. Either way.
Just to build on my last question, how do the students respond to using these tools?
I've been really happy with how the students respond to the notebook style tools. And I find a lot of students, the things that have surprised me is over the years, I've found myself doing two things with the introductory class. One is running my own server that I can, again, just give the students an account on. and have a Unix interface that again, there's one way to teach it to the students. As long as I can get them logged on from everywhere on, it's one thing to tell them, compared to everyone's got their own locally installed setup that we've got to debug things 30 times every class. That kind of ease of use makes it easier for the students too. It certainly makes it easier for me, but I think it means it's a much more consistent experience for the students. And they this kind of hacked up system of the idea of working directly with the machine at a Linux level. I've repeatedly had the students tell me it feels like they're really computing in a way that something like Eclipse doesn't to them. So I was very surprised by that. Again, for my upper level students, they've been doing this a while. They've taken a data science class here or there. They know that notebooks are the way the field is going, and they're just very comfortable with it already.
Any other final questions for Dave?
Thanks, Dave.
Sure, thank you.
Well, Dave, thank you very much for this. Has been very interesting, and I can see a wide range of applications of this environment. So I hope people found it useful. So thank you again. Yeah. And thanks those who joined today, and everybody have a nice upcoming weekend.
Thanks for organizing, Steve.
Thanks.